Hi there. Today I'm going to go through the LeetCode problem 269, the Alien dictionary. So for this question, it said this is a new alien language which use Latin. Okay. However, the older among letters are unknown to you, you receive a list of non-empty words from the dictionary, where the words are sorted lexicographically by the rule of this new language. Okay, derive the order of letters, later, letters. Okay, never mind. Sorry, in this language. Okay, we go through not go through. Yeah, go through the example one first. Let's see how we got this results. Okay, so it said the words are sorted lexicographically by this rule, and the order among the later are unknown to you. It confused me at first, but okay, let's we go through an example first. So we compare the first word WRT, WRF, and we know both W as the first character is the same, R is the same, and T is before the F, so we got TF. And then we compare the next words, TRF and ER. So we got W is before the E. Okay, this is our second relationship. And go through ER and ETT. And the first character is the same, so we compare R and T, and R is before the T, so we got the relationship R is before the T. And we compare these words and these words, and the E, the first character, they are not the same, so we can get the order. E is before to R. So this is what we got from this input, and from those relationships we need to get the output is the WERTF. So let's see because and okay, right now we got those relationships by analyzing the first example, right? But before we go deeply about this problem, I wanna introduce the algorithm first. Is a topological sort. Topological sort is a directed graph, which is a linear ordering of its vertex, such that for every directed edge U from the vertex V, U comes before the U. V in the ordering. So let me give you an example. So in this graph, we have a 4, 2, 2, 2, 4, 2, 2, 3, and 2, 2, 2, 0, and 2, 2, 2, 1, 2, 3, 2, 2, 1. Okay, so we have a 5 different way to get the order of this graph. 4, 2, 3, 0, 1. Okay, but every order over here, they follow the rules. 4 is before 2 and 3. 2 is before 0 and 1, you can see. And 3 is before the 1, right? All the five sequence follow those rules. So how can we get those problem? Not problem. How can we go this sequence? Okay, by implement the topological sort, we have two ways. One way is BFS, and another way is DFS. So let me introduce the BFS way first. So you can say over here, 4 is a source, right? We can say it is a source because we don't have any other vertices. It's coming from 4. We don't have it, right? We don't have it. So 4 is the sources. So 4 can be placed in the first position, right, over here. And we can define a terminal for this situation, like from one node to another node, and for example 4 to the 2, and which means 2 have a 1 in degree because we have one line over here. 4 is go into 2, right? And and for 3 we also have 1 in degree, right? And for 0 we have 1 in degree is from 2, and for 1 we have 2 in degrees. 1 is from 2 and 1 is from 3, right? And so what's those integers for? How should we use those integrals to figure out our problem? Okay, let me go through this graph. So we know we have for BFS, we will implement by a queue, right? Okay, never mind. By a queue. So because the integral of 4 is 0, so we can push the 4 into the queue. Okay. So follow the DFS rules. We should traverse everything in the queue, right? Because sorry, we pop 4 from the queue and we minus the integral is from 4. So we by 1 because over here we already take out our 4, right, in our list. So for 4th children, 2 and 3, we can decrease their integral by 1. So for node 2 and node 3, they can their integral is already 0, will become to 0 because we take out the 4, right? So the 2 and 3, the integral is 0. So when the integral is a 0, this means we can push those nodes into our queue, right? This is our result. We can push 2 and 3. And then our current node will become to 2. And for 2's children, we only have 1 node is from source 2, which sorry, which is node 0, right? And for this 0 node, because we take out of our 2, oh, not only one, my bad. We have 2 nodes, one is 0 and one is 1. Okay, so we decrease the children of 2 by 1 integrate, right? This means for our 0, we don't have integrate go to 0. And for our 1, we only have a 3 as an integrate to our 1, right? So for this, and right now, our 0 have a 0 integrate, but our 1 only have one more integrate. So we push our 0 into our queue. And right now, result is we become 4 and 2. And the current will pop out from the queue, which is a 3. So for our 3. Now for 3 children, so it's a 1, right? So we can cross out this integrate for 1. So 1 finally have a 0 integrate, and we can push it into the queue. And we pop out 3, add into our result, and I'm pop out 0 do not have any children over here. And for 1 is do not have any children, so we got the ordering is a 4, 2, 3, 0, 1. This is for this example. And I have one more question, is that what if we have a cycle in our graph? Can we got this order? Sorry, the answer is no, because you need to remember when we push something into queue, which means their integrate is 0, then we push the nodes into queue. But take a look over here, I add an edge from 1 to 3. So 3 to 1, 1 to 3, 3 to 1, 1 to 3 is a cycle, right? Which means when we first push the 4 into our queue, and our current, popped out from queue for queue is 4, and we can only decrease one integrate is 2 have a 0, so we push the 0 into our queue. And for 2, we take it out. So our result over here, our result here is a 4. And we pop out 2 from our queue, and this integrate is decreased, is 0, and this integrate, the one's integrate is 1. So, but 0 is 0, 0's integrate is 0, so we put it into queue. It sounds weird, sorry. Okay, our result is 2 over here. And we pop out our zeros out. Our 0 do not have any children, and we add the 0 to our results. And our queue is finished, right? Queue is finished, but we never get touched to the nodes 1 and node 3. We lost those data. So which means if we got the results from our graph, the length of our result is not equal to vertex of the graph, which means we have a circle, not cycle. We have a circle in this graph. Okay, so this is BFS way to implement our topological sort. Okay, since I already introduced the BFS way to figure out the topological sort, and let's go back and take a look at this question. And over here, we already get those relationships, right? Which means we can figure this problem out by the topological sort and using BFS way. So what should we do about this question first? Okay, first we know it's a parent. It's a graph problem, right? So first we need to construct a graph, and I already said the using BFS way, the most important thing is we need to find out the integrate. So integrate. First, construct the graph. Second, found out the integrate. And the 3 is push the nodes integrate equal to 0 into our queue. And the 3 is a process nodes while the queue is not empty, right? And every time and when we get process the nodes in a queue, we define it as a current node, and we take out the current node, add into our result, add current nodes into our result. This is the first thing we need to do. And second thing is that we need to decrease the one integrate of current children nodes. And the third thing is that if one of the child's integrate equal to 0, then we push it into queue. So this is the process. How should we figure out this problem? By BFS. And one more thing we need to check is that we need to check the length of results is equal to the vertex or not. is not equal to, which means the graph has circle, which means we need to return empty string over here for this question. So this is the process of the program. This problem figured out by the BFS. So I'm going to show my code over here. Okay, this one is for edge case, and we need to define our integrate, which I defined by hash map. The key is character, value is integer, and the graph. The key is character and at end, and the value is a list of character. So I have a string builder because our return value is a string, and we do by the BFS way over here. Okay, let's go through our BFS. Okay, there is a method, hyper method, to help me to construct my graph over there. So let's go to the BFS directly. So in a BFS, we return the string builder. So I have a queue over here. And first, I will add the integrates. I will add the loads with integrates equal to 0 into my queue. Okay, and over here, the while loop, while the queue is not empty, we will do the A/B thing stuff, the 3 steps in my queue. First, we got the current character, and we append to our results, and we got the children of our character. And do the for loop. Doing the for loop because we need to increase 1 degree for those children, and we also need to check if one of the children's integrate is equal to 0, and we push into Q. So this is basically how should we fix the topological sort by the BFS. Okay, let's figure out another way by using DFS thinking to help us to find out the topologic ordering. Okay, so we in DFS thinking, which means we need to traverse every vertex, right? But during the process, we traverse the vertex because we are finding a parents' children list, and doing the DFS way recursively. So we have to mark those nodes we already visited. So over here, I use the hash set or set to mark my nodes, which is already visited. So okay, let's begin at 4. Okay, before I go through this example, I want to define the term, because in our topological sort, 4 is before 2 and 3, 0 is before 2, 1 is before, no, 2 is before 2, 0, and 2 is before 3, 3 is before 1. So let me define the 4 is a parent of 2, 2 is a parent of 0 and 1, and 3 is a parent of 1. Okay, so let's traverse it first. So when we traverse 4, we can go either way, go 2 and 3, or 3. So we go to this side, go to the 2 and go to 0. Okay, 0 do not have any children, so we can add 0 into our list. and I will already visit finished on 0. Right? And till have another children is 1. So 1 do not have other children, so 1 is finished. And go back to 2. And since all the children of 2 were already traversed, so 2, we can add 2 into our results. And since 4's left children will finish, we can go through the right children of 4, which is 3. Because we can add 3 over there directly, so we have another children is 1, but when we traverse 2, we already traversed down 1. So in our visited, we can have 1, 2, 3. And the last step, 4. So you can say this list need to reverse because we implemented it by recursively. So this result need to reversed. So we got our right ordering. We met we got a problem if we just simply implement our solution by this way. So think about it. How about in our graph we have a circle like this one. 3 can go to 1, 1 can go to 3, 3 can go to 1. 3 is the parent of 1, 1 is the parent of 3. So how should we figure it out? Okay, so how about we add the state for my each node? Let's go back the last example we do over here. I add a visited hashes map for my visited nodes. I just simply add it to our visited set. So, but how about I remember or define some stages for my visiting, for my visit process. Like if we are not visited nodes, we defined is 0. 0 means we not visited. We haven't visited it yet. 1 is the processing we are visiting. We are visiting is this node. 2 is a stage represents. Okay, we finish visited this node. Okay, let me traverse this example with a graph. Have a circle using our visited stage. Okay, we begin with 4. 4 we as an initialized stage, all the nodes should be not visited, right? It's 0. So we determined. We can determine it. Okay, so for the 4, the stage is 0, which means we can start visited. So we change the state for 4 is 1, and go DFS things. Go to 2 or 3. We go to 2 this side, and then for the 2, the stage is 1, right? Because it's not finished. It's visiting. We have two visited 2 children, which is 0 and 1. So for the 0, okay, 0 for now is 1, but 0 do not have other children, so we change it to 2, which means, oh, we finished 0, visited 0 these nodes, so we can add it into our result. First nodes we got. So we go back, and to have another structure is 1. Okay, we change to 1. First we check. We definitely need to check the stage. For 1 stage is 0, so we can change it to 1. And 1 have children, which is 3. So we go to 3. Okay, 3 is never visited before, is 0, so we change the stage 3 stage to 1. Okay, for 3 we have children. Oh, it's 1. We check the 1 stage, and we already find it's 1, which means we find a circle over 3 and 1, which means we cannot do topological sort for this graph. So this is a process. The second example is a process we implement our topological sort by DFS thinking, by adding stage in DFS way, right? We already know how should we figure out the topological sort by DFS way. So let's go back to our question, Alien dictionary, to think about how should we implement it. So for our DFS, let's recover it. So first thing is that we need to define our stage, right? Defined nodes visited stage and do DFS, right? And over here, I want to share my code to explain it. Okay, here's my code how I implement this question by DFS way, DFS thinking. So for the first part over here, I need to define my stage, right? Visited stage. I implemented by hash map. The key is a character and the value is integer 0, 1, 2. And over here I construct the graph. Oh, okay, I have another variable is the characters, because as I said before, because the DFS, since we need to traverse all the all the character in this word, but by the example give me, we don't know. We have how many characters in a total word, so we need to traverse it. We need to write it down, right? And string builder, okay, and okay, this is our things. Traverse all the character over here, and if the visited is equal to 0, that means we never visited before. So we can do our help method. Our help method is a recursive call over here. The input is a graph, and the visited hash map and string builder, and the character which we are current visited. And the return type is a boolean. If it's false, this means in our graph we got a circle. We got a circle like that, as I traversed the example before. So at first, in the recursive call, we need to check the state. If the state is 1, which means we are visiting during the processing of visiting this node, and we come back again, which means we have circle over here, so we just return false directly. If we got the node is 2, which means we're already done these nodes, we don't have to, we return true. And we put the current nodes into 1, which means we are during the process of visiting the node. And over here, this is the DFS way. Do the same things for this current node's children. And after we do this, finish this stuff, we can put our current characters too, which means we finish down, we visiting down, and we can append this character to our string builder, right? And a very important thing over here is that the return things is a string builder reverse to the to string. So because we implement these things by recursive code, right? It's like a bottom up things. So we need to reverse it. Okay, this is a really long question. That's it. This is a question for this week. I thank you guys. Bye.